In the second part of chapter 4, we are going to talk about doubling time and half-life. So let's take a look at the formula for doubling time of an exponential model. Let's say that you have a petri dish in which there are 300 bacteria. So the initial value is 300 bacteria. Now, when we talk about doubling time, what we're essentially asking is the following. How long does it take for the bacteria to double? In other words, if y represents a number of bacteria, at which t is the number of bacteria equal to 600. Where did we get 600 from? Because we started off with 300 bacteria, double of that is going to be 600. So after how long do we have 600 bacteria? Now, A is going to be the initial amount. T is going to be the time, and D is the amount of time taken to double. Okay, so where D is the amount of time taken to double. So here's an example. Under ideal conditions, a certain bacteria population is known to double every 5 hours. So remember, the doubling time is going to be your D value. So in this case, your D value will equal to 5. Suppose there are initially 800 bacteria. So we know that the value of A is 800 because A is always our initial value. So the question is, what is the size of the population after 15 hours? So what we know is every 5 hours, the bacteria doubles. So what is the size of the population after 15 hours? Well, so our equation is going to be y equals to A times 2. Now, the reason we have 2 is because, remember, we're doubling the bacteria. So that's why we have a constant of 2. And then that's to the power of T divided by D. That's our formula. Now, let's use this formula and plug in what we know. Okay? So we're looking for y. We're looking for how many bacteria do we have. If the initial number of bacteria is 800, we have a constant of 2 because our doubling time, because we're doubling. Now we want to know the population after 15 hours if the doubling time is 5 hours. So T is 15, D is 5, D is a doubling time. So we just plug this in. If I simplify this, 15 divided by 5 is 3. So we have 800 times 2 to the third power. Remember the order of operations, we have to do the exponent first, but what I recommend is just putting this in the calculator left to right the way we see it, 800 times 2 cubed, and then this will give you y equals to 6,400 bacteria after 15 hours if the doubling time is 5 hours. Here's another way to look at it. The initial, so at time equal to 0, the number of bacteria is 800. That's our initial value. Now, every 5 hours, that doubles. So after 5 hours, if you double 800, that's 1600. Now, after 10 hours, because every 5 hours, the number of bacteria doubles. So after 10 hours, you take 16 times 2, that's 3200. It doubled again. Then 5 more hours pass, T equals to 15. If you double 3200, we get 6400. So at T equals to 15, we have 6,400 bacteria, which is the exact same thing we got using the formula. Part B says, what is the size of the population after T hours? So now here we want a generic formula. Y represents the size of the population. We know that our initial value is 800 times 2 raised to the power of T divided by 5 because our doubling time is 5. So all we're doing is we're plugging it into the formula, but we're going to leave T as a variable. And then part C says, estimate the size of the population after 19 hours. So once again, we're going to replace T with 19. So we're going to say y equals to 800 times 2 raised to the power of 19 divided by 5. And what I recommend is you put this into a calculator just the way it looks, including the parentheses, and this will give us 11143 bacteria after 19 hours. Now let's talk about half-life. The half-life of x is the amount of time it takes for x to decrease to half the original amount. So this is the key. Half the original amount. Half-life is the time it takes for the initial amount to decrease to half the original amount. Now let's do a quick refresher of the properties of exponents. So let's say we have log of a to the n. We have an exponent when we take the log of a base of a power of n. That n always comes to the front when we're dealing with logarithms. So this becomes n times log of a. To solve an equation in which the variable is an exponent, we have to take the log or the natural log of each side. So for example, let's say I want to solve the equation log of 2 to the x equals to 8. Anytime my variable is an exponent, like in this case, my variable is an exponent. Oh, I'm sorry, you know what? Let's not take the log yet. We have the equation 2 to the x equals to 8. So the variable is an exponent. To solve this equation, we would need to take the log of each side. Take the log of the left side and take the log of the right side. So now what happens is, according to this property, that x comes to the front. But that only happens for logarithms. It doesn't happen if we just have a normal 2 to the x. But when there's a logarithm involved, the x comes to the front. So we have x times log of 2 equals to log of 8. And now the x is a coefficient. So this is a multiplication problem, which means to solve this, we would divide both sides by log of 2. And in a calculator, you would plug in log of 8 divided by log of 2, and you would get x equals to 3. Please practice that on your calculator. The way you would put these in different calculators is a little bit different. So make sure you do this problem and end up with x equals to 3 when you plug this in. Okay, so let's take a look at our first example. A doctor prescribes 200 milligrams of a therapeutic drug that decays by 35% each hour. What is the half-life of this drug? Now, let's have a quick reminder from the first part of chapter 1. Anytime we have exponential decay, the equation is going to be y equals to a, which is the initial value, times 1 minus r raised to the t power, where r is the rate of decay and t is time. So in this case, a doctor prescribes 200 milligrams, so this is the value of a, that's our initial value, and it decays by 35% each hour. In decimal form, 35%, that's going to be 0.35. So you have y equals to a, which once again is going to be 200 milligrams. Times 1 minus r, which is going to be 0.35. And then that's raised to the power of t. So t is time, and that's what we're trying to find. We want to know after how long does this initial amount decrease by half. Now half-life, remember by definition, it's the time taken for x to decrease to half its original amount. So if the original amount is 200, then the value of y is going to be half of that. So for half-life, we're going to take the initial amount and divide that by 2, which is 100 milligrams. This is going to be the value of y. So y is going to be 100 milligrams. Why is that? Once again, because we want the half-life of 200, which is going to be 100. So we have 100 equals to 200 times 1 minus 0.35 to the t power. Let's simplify this. So you have 100 equals to 200. 1 minus 0.35 is 0.65 raised to the t power. We divide both sides by 200. So 100 divided by 200, that's going to give us 0.5 equals to 0.65 to the power of t. Now, this is where the properties of logarithms come in. Remember we learned that if your variable is an exponent, we take the log or the natural log of each side. Either one works. So in this case, our exponent is a variable. T is what we're looking for, and that happens to be the exponent. So what we're going to do is we are going to take the logarithm of the left and right side. That's how we solve any equation where the exponent's a variable. So I take the log of the left side and I take the log of the right side. Now what happens when I do that? When I take the log of the left side, let's go up here, it just becomes log of 0.5. When I take the log of the right side though, this t comes down. That's the whole point of taking a logarithm. That t is going to come down and this becomes a multiplication problem. So we have t times log of 0.65. Now, since this is a multiplication problem, we can divide both sides by log of 0.65, divide by log of 0.65. Now, depending on what kind of a calculator you have, you'll have to, just know how to input this because every calculator is a little bit different. But what you should get is 1.61 hours approximately. So this tells us that after about 1.61 hours, the 200 milligrams will decrease to 100 milligrams, half the original amount. Now, part B is unrelated to half-life. It says, what is the amount of the therapeutic drug left after 10 hours? So we know that our general equation is going to be y equals to the initial value, which is 200, times 1 minus 0.35, which is 0.65 to the power of t. And in this case, t is going to be 10 hours, so we just plug this in. We have 200 times 0.65 to the power of 10. And if you plug this in, you're going to get 2.69 milligrams. Okay, let's do one more example. In 2015, the population of now these numbers are not accurate, but in 2015, let's assume the US population was 157 million and it was growing at a rate of 0.5% each year. Now, anytime we have exponential growth, our equation, our generic equation is going to be a times 1 plus r to the power of t. Now the question is, in what year will the population reach 271 million? Okay, so first, let's just come up with a generic equation. We know that the initial population is 157 million. So we're going to have y equals to 157, and I'm going to leave out the million. I'm just going to say 157, and we know that it's in millions, times 1 plus the rate. Be careful with the conversion. So if you take 0.5% and you convert that into a decimal, we have to divide that by 100, which will give us 0.005. So r in decimal form is going to be 0.005. And that's to the power of t. Now we want to know in what year will the population reach 271 million. So the value of y is going to be 271 million. So I'm going to replace the y value with 271. That equals to 157 times 1.005 raised to the power of t. Okay, now first step, we're going to divide both sides by 157 because I want to get that parentheses by itself. And when you have any kind of a middle step, keep at least 6 decimal places. So this is going to give me 1.726115 equals to 1.005 to the power of t. Then we take the logarithm of each side. Anytime the variable is an exponent, we have to take the log of each side, just like with the previous examples. And in this case, our variable happens to be an exponent, so we take the log of each side. On the left side, we're left with just log of 1.726115. That's 271 over 157. And then on the right side, the t comes down, so we have t times log of 1.005. Okay, and then finally, we're going to divide both sides by log of 1.005 because you want to get that t by itself. And if you put this in a calculator, you're going to get t equals to 109.45. But that wasn't the question. The question was, in what year will the population reach 271? Now, our base year is 2015. This is where we start our initial value. Now, after this, 109.45 years have to pass. So I'm going to add to this 109.45. If I add that, I'm going to get 2124.45. Normally, you would round this to 2124 because 0.45 you would round down. However, if in this case that would be incorrect because by 2124 the population has not quite reached 271 million. It reaches 271 million at 2124.45 years, so almost half the year has to pass. So if you round down, we haven't reached 271 million. So in this case, you would round up to 2125. Okay, and then this last problem we are going to skip because it's very similar.